Okay. Good evening, everyone. Today we are going to learn a little bit more about the spectroscopy, what we have started in the last class. And in last class, we have learned how we can get the qualitative information or how we can perform the qualitative test using the UV spectrophotometer. And today I have mentioned, in the last class I have mentioned that this class will be how we can perform the quantitative analysis for the UV spectrophotometer. That means how much sample or what is the quantity, how much amount of any substance you have in your sample we can study or we can analyze by using UV visible spectrophotometer. So here we have two different types of uses for the UV visible spectroscopy: qualitative analysis and quantitative analysis. So you are familiar with the two words. Quality, that means what is the inside what, and quantity, that means how much. So last class we have learned about the instrumentation, and from there I will show something. What happened? My this is not working. This. I have shown that this instrumentation, and I have mentioned that this is our sample cuvette and this is our reference cuvette. That means here we will have only the solvent and here we will have the sample with solvent. Okay, if we have different size, if we have different amount of solvent or substance, let us consider we have 1 milliliter of the sample and another cell we are using different length cell length 1 millimeter, not 1 millimeter, this is too small, maybe 5 millimeter and 10 milliliter. If we have cell of different length, if we have the cell one with very thin, another one little bit thicker, let us consider this is around 1 centimeter, that means 10 millimeter. Is it 10 millimeter? And another one will have just 0.5. I'm expecting that should be around 5 millimeter. Okay. So if this is the cell, that means we have just here the cell length. If we consider, if we have more amount of sample, in that case, we have mentioned that how much light we are detecting here. That is the amount of light what has been passed through this. Is it? That means the remaining after absorbing. We have given the light from here, and some of the light is absorbing by the sample, and rest of the light is going to this detector. Here also same thing. If we do not have any sample here, then we will get the same amount of light here and also here. Okay, so if we have one situation where we have 5 millimeter cell, or that means a small amount of sample, and we have another cell with 10 milliliter. In that case, that means we have more sample. So what do you think? Should we see the same intense light? Then what should be? We should see different, and you can guess. That means if you have more amount of sample here, in that case we will see less light. Is it? Very simple. I have one very simple thing. This is a plastic, and I have, if you see the light intensity, this is normal. That means this is when we are passing the light. Here we have solvent, this is solvent. Okay? If we have this solvent and solvent, all of them are same, then you will see just this bright light. Exactly. If we have a small amount of, that means a small amount of sample, that will absorb little less, sorry, little amount of light. So it will transmit most of that. So if I give, now you can see transmitted little bit less compared to this one. If I go like this way, so you can see that the brightness of this light is more, but if I go through with sample, that means the thickness of this sample is little bit less. Therefore, we can see some light. But if I go little bit thicker region, what about? Yes, even I have the option for even thicker. Now you cannot see anything. Is it? How I made it? See, this is a just plastic bag, little bit thicker. I have cut one part. So here I am giving the thickness 1. I am coming here, this is the packet, just double layer. So I am making double layer and I have folded it so that I can make it three layer, triple layer. So if you have less amount of sample here, in that case, you will observe more light. That means less amount of light is absorbing. If you have more sample, that means more thicker sample or more amount of sample. In that case, it will absorb more light and you will get less amount of light in the detector. So, as we increase the sample, in that case, we will absorb less amount of light. That means absorbance will high and transmittance will be less. So, that is the formula what we are going to learn. That means to determine the concentration of any sample. Understand? That means if you have more amount of sample in any reservoir or in a cuvette, then more absorbance, less amount of transmittance. So if we consider this is the path length which is directly related to the amount of sample. So if the path length of the cell is bigger or higher, in that case, absorbance will be higher, but transmittance will be lower. So we are getting that the absorbance of the light to the sample is directly proportional to the amount of the sample or path length. That means if we increase the length of the cell, more amount of sample will be there. So we can easily consider that the more amount of sample is here, so it will absorb more, so that the concentration or the, so if it absorbs more, what I am going to show you, that will be my formula. This is too large. This is. So if we consider that the absorbance, if we do not have any sample, then what we will see? No absorbance. Exactly. That means it will transmit 100% light. In that case, we can have a point. That means this is the concentration. If we plot a graph against a, this is concentration and absorbance. Let us consider we have several data like this. Concentration of the sample, maybe orange juice or mango juice, what I have mentioned in the last class. So let us consider we have absorbance, sorry, concentration versus absorbance. So 0 concentration, absorbance will be 0. Simply because if there is no sample, then it will transmit all of the light. So absorbance will be okay. That will be this point. Then if we have certain amount of sample, very small amount, let us consider 0.01 molar. In that case, the absorbance will be little bit high. Let us consider just 0.1. Approximately, I do not know what would be the sample, but I can guess like this. If we have that, can be this is x-axis, and then along y-axis that can be. Similarly, as we increase the concentration of the sample, that will increase the absorbance. As already I have shown you that if I pass the light without any medium, without any sample, in that case we can see all the lights. It will go as just single layer. This is my single layer, and here I am moving, and this is double layer, and this is triple layer. So as we increase the light, as we increase the concentration, absorbance will be more. 0.02 molar, 0.04, 0.1, something like this. In that case, we can have 0.2, 0.4, 0.1, 0.4, that should be 1. Like this. In that case, if we plot a graph like this, that will give you a straight line. A straight line passing through the center. Just this point, this point, this point, and this point, like this. That means by this way, you can prepare a standard curve. What is means a standard? If you know some concentration for any solution, that is known as a standard. Is it? Then a standard curve means you have prepared that different types of sample. You have taken the absorbance from the UV visible spectrophotometer, and you have plotted these types of curve that will give you that is known as a standard curve. Now you have certain sample, you do not know the concentration. Then what you will do? If you do not know the concentration for a certain sample, then already you have prepared these types of standard curve. Now, if you have a sample and you take the UV visible spectrum, then you will know the absorbance from your instrument. Now, if you know the absorbance, just let us consider this is our absorbance, what we found from the instrument. That means you are getting like this way. So we'll get this is the concentration value. So that is the principle how we can estimate the concentration of any sample. First, you need to prepare a standard curve. Then you can find out what is the concentration of your unknown sample. So you need to know what is the sample, and you need to prepare some standard solution, and then you will prepare a standard curve, and then you can have some other sample, but concentration you may not know. So after getting the sample, sometimes it may be difficult to have the concentration because you have a standard curve in this range. That means what I have shown only this range 0.01 to 0.1 molar. But your sample may have very high concentration. In that case, our instrument has some limitation. What is the limitation? I have mentioned as a deviation. I maybe later I will discuss little bit, but I'm going to. So our instrument works linearly only in the range of absorbance. If you have the absorbance only in the range of maximum 2. If you have any value for absorbance beyond less than 2, you can get that data, and instrument will give the exactly the information. So if you have any sample with very high absorbance. In that case, you cannot rely on the instrument. So what you will do then? How? Yes, that is the way. Just take a very small amount of sample, maybe 1 milliliter or 5 milliliter, and then dilute it. Then you can take the absorbance so that you can get the concentration, and then you need to multiply how much you have diluted. That is the ultimate way. Even sometimes you may have some sample, you don't have the even this range or below this range, very far away, maybe 0.001 like this. That's also very difficult because if all the lights transmit, that means absorbance is very little. If you have very small transmittance, very high transmittance and very little absorbance, in that case, it is very difficult for the instrument that how much it has been absorbed. Maybe within 100%, if 90%, 95% or 99% transmit, so only 1% or 0.5% if it absorbs by the sample, in that case, it may be also have some problem. So that the absorbance, what we are getting, that can be wrong result. In that case, what we have to do? Not double the amount. One way you can say, by doubling the amount, in that case, you can increase the cell length. That way, but for some instrument, we have some limitation that we cannot increase the cell length. We have some limitation. Maybe we can use 5 milliliter or 10 milliliter or approximate 1 centimeter. But beyond this, in that case, we can increase the concentration by evaporation. That means if we previously what you have mentioned that we can dilute it. Now you can evaporate the sample and then residue. You can take 1 liter of the sample, then dry up or heat up, make it 100 ml or 10 ml. That will give you the concentration 10 times more, 100 times more. Okay? So, if we can increase the concentration by reducing the volume of the sample, by how? By dry up. Because different types of solvent can dry up easily. So, by that way, we can reduce the amount of the solvent, or we can increase the concentration. Therefore, we can have the absorbance for the. Can we come near the laptop? Okay. Yes. Yeah. Even there is another problem that if I can take the cable from a little bit far away, that could help me, but that is not possible because the length of the cable is limited. I can extend my leg a little bit, but I cannot go very far away. Anyway, so any of you have the problem? How we can determine the concentration of any sample? Everything is fine? Okay. So now we have already, I have mentioned the law for the UV visible spectrophotometer, which is known as Beer-Lambert law. Already I have discussed. That means that is dependent on, I have mentioned about the path length. If you have the path length, just path length, that means amount of directly related to the amount of the sample. So units of the, not this, I should go, the laws of the spectroscopy. There are two main laws. So we call it Lamberts law and Beer's law, and when we combine it, that gives the Beer's-Lambert law. So Beer's law and Lamberts law already I have discussed that if you have the cell length constant, if you have the cell length constant, in that case, the absorbance of the sample is directly proportional to the concentration. So if the concentration of the sample is very high, the absorbance will be high. So absorbance, what we mentioned like this way, absorbance is directly proportional, A is proportional to the concentration. So absorbance is proportional to the concentration if the cell length, that means in which cuvette we will take the sample. If the cell length is fixed, in that case, the absorbance of the sample will be directly proportional to the concentration of the sample. Now, if we have a specific concentration, certain concentration, so if we have the concentration fixed, in that case, if we take the very small cell, we will have very small amount of sample. If we have bigger cell, we can have more sample. So that is directly related to the, that means absorbance is related to the path length. That means cell of the length, cell length. I'm writing. Okay. So if the absorbance, the path length is there, the absorbance will be directly related to the, or directly proportional to the concentration. And if the concentration is fixed, that means here we consider that L fixed. Okay. And if we consider that the concentration is fixed, then absorbance proportional to the cell length, that means C fixed. Now, if we consider both are variable, in that case, we can combine that absorbance, that means A is proportional to the CL, and if we want to remove the proportionality constant, we need to multiply and certain constant factor. So that is called as A equal E, or sometimes some people write down like this way, PCL. So this is the proportionality constant. What we call it absorptive constant. So that is the relation. That means we are Lamberts law. So if we have any sample, so what I have mentioned, that means to determine the concentration, unknown sample, I have shown you that graph, this one. That is in terms of if this one is constant, that means L is constant. So when we want to determine the concentration of unknown sample, we need to fix the length of the cell, so that if we can take different concentrated sample in our cell, then we can absorb different absorption, and we can plot a standard curve against the concentration. By plotting this way, then if we have unknown sample, we can have the absorbance that can be even, you can have even larger. That is also possible. And sometimes, but try to keep, when you are having the experiment, try to keep your standard sample range in this region, so that your unknown sample is do not beyond the standard curve. So try to keep, you can keep the standard curve little bit higher. Even I have mentioned that 0.01, 0.02, even you can take even higher concentration, maybe 1 molarity like this. In that case, you can have a concentration absorbance maybe here also. So just try to keep your concentration, that means unknown concentration. You may have the absorbance value from your unknown concentration. So you can guess how much concentration I may need to plot. So by this way, we can estimate the concentration of any sample using UV visible spectrophotometer. Okay. Any question? Okay. What I wanted to show in the last class, we have mentioned that electromagnetic spectrum, and that is related to the wavelength and the energy. All the electromagnetic spectrum, what I have shown here, sorry, that one, I think I should clean up. Any problem? Any problem? Okay. Last class also we have discussed about the electromagnetic spectrum a little bit, but I did not show these types of graphs. That is very interesting because as you see, it is compressing from left to right. What does it mean? That means this, you can see this is the wavelength. You are familiar with the term wavelength, frequency, is it? So here you can see that the wavelength, what would be? From here to here, is it? This is the wavelength. Or even from here to here, this is our wavelength. So if you consider that for radio wave, that means this region is our radio wave. So the wavelength for this radio wave is very big. So when you go little right, the microwave, the wavelength becomes little bit shorter. Infrared ray again short, visible again short, ultraviolet again short, X-ray even shorter. So that graph is very technically drawn because this is related to the wavelength and this is related to the energy. So here the energy, as the wavelength large, the energy is large. Sorry, low. So here, as the wavelength is longer, last class I mentioned one number 1239.85. That is a constant. If you divide that number with the wavelength, that means this is our wavelength what we are mentioning. So if we divide that number with the wavelength in nanometer, then you will get the value of energy for that wavelength in electron volt. So here, this is the very long wavelength. It has the minimum energy, and as you go from left to right, you can see that means the infrared ray is little higher energy compared to the microwave. So this microwave and radio wave, these are used in the different types of television and radio or mobile phone, this type. So these are very low energy and it do not affect too much to our body. Therefore, everywhere the waves are, so that wherever you go, you can catch your mobile phone or you can catch the signal from the television. So that length, that radio wave are everywhere in the universe. So we can catch the radio wave with our signal receiver. And this is very low energy. And as we go from left to right, we are increasing the energy. We are decreasing the wavelength, we are increasing the energy, and this is frequency. Okay, frequency, that is also frequency, last class also mentioned, that means any event happening per second. That means what are the events, how many events in 1 second it is happening, that is the frequency. So just any question? Okay, so frequency, as we go from left to right, the frequency is increasing like as energy. That means you can consider that the energy is proportional to the frequency, or other way, the frequency is proportional to the energy. Okay. The strength of the radiation energy will interact with the molecule in different ways. That means what energy, sorry, from here, which wavelength we are giving to the molecule, that will determine the energy. And if you give high energy, the molecule can be decomposed or it can vibrate. Maybe if you consider I am a water molecule, my head is oxygen and these two hands are hydrogen. So water molecule like this way, bending. So that means it can move like this way, is it? Or sometimes it can go like this way. Okay, so it can go stressing or bending like this way. So if you give different amount of energy, what wavelength you are giving to the molecule, depending on that energy or that wavelength, that means if I consider wavelength, that corresponds to some energy, is it? So if you put some energy to any molecule, that will determine how the molecule will behave. That means if I give this energy, this microwave, in your home, all of you have microwave, is it? So this microwave can heat up only the water molecule, not any other. If you put this plastic bag inside the microwave, it will happen nothing. No, it will not melt. It will not melt. Just if you have only water inside the microwave, that can heat up the water molecule. Because water molecule, if you have anything dry food, that will not heat up in the microwave. Just it can heat up, it can increase the vibration, because water molecule is vibrating completely like this way, and the energy what you are giving this microwave, that energy corresponds to the vibration energy of water. So that energy can excite the vibration mode of water. Therefore, the only water molecule can be excited in the microwave. If you put anything else, that will not heat up. Okay? What?
I'm just saying, like when you put like something in a microwave, like the ball itself, also they put it, the plastic ball, they put it up.
Because it contains the moisture.
Oh, the plastic.
Yeah, plastic bag, if it contains moisture, if you first dry up your plastic bag.
And the plastic container.
Yeah, plastic container. That means it is taking water, is containing the water, actually heat. Then this heat is transmitted to the plastic cup or whatever. But if the plastic, that means ethylene, polyethylene, is it?
Yeah.
Polyethylene, what we write down? CH2, CH2, and then this is our polyethylene, is it? If this is the molecule, it will not absorb the microwave. No way. Because the mode, vibration mode of this molecule is not related to this microwave. To excite this molecule, you need to apply higher energy. Maybe this one. Okay? So, if you give this much energy, or at least this much energy, that can help you to excite this molecule. So depending on the energy what we are giving to the molecule, that will determine how it behaves. So here, high energy sources produce breaking of bonds. That means what I have shown, X-ray, this X-ray. This X-ray or gamma ray, these are very high energized because as I have told that the wavelength is very short. Therefore, this X-ray and gamma ray, this is very high energy. Therefore, doctors suggest you not to have the X-ray very often. Is it? Because the X-ray can damage your cell. So that not very often, sometimes we must need to have to determine the disease or what type of problem you have. So we may need to have, but you should not take it very often. So this is high, very high energy, even this even higher. So we should, so these are little bit lower compared to this. So if we put this much energy to any molecule, we are giving to our body for getting the image of the bone or whatever. So that means this high energy electron or high energy wavelength, it can penetrate. It is so high energized that it can penetrate through our body. But if I give this light, it cannot pass through my just this hand because this is visible. Is it? This is visible, so it has the moderate energy, not very high. That means this energy is very low. This is little higher. This is little bit even higher, but still in the not very high range. So if we put this energy or this wavelength, it cannot penetrate through my hand. So if we put this light, that can, so if we put this energy, it can decompose a molecule. That means if we put this X-ray to any water molecule or different types of molecule, it can decompose its bonds completely. Even if it is possible to take an electron from the core of the nucleus. That means this is maybe sodium atom. We have electrons here. We have 8 electrons in the second cell. Last cell, 1. So if you give X-ray to this sodium molecule, sodium atom, in that case, it can take up electron from this shell also. That means for ionization energy, you know the definition of ionization energy. Ionic potential, energy required to remove one electron from this atom. That means what will happen if you want to take one electron from one metal or some atom, that will take up only the end up or outermost shell electron. That means just enough energy to remove one electron from the outermost shell of the atom. That is known as the ionization potential. And most of the time for any organic molecule, the ionization potential is around 10 electron volts. Around. It can plus minus 2 or 3 electron volts also. So if you want to remove, or I have worked with the molecule I have mentioned last time. Can you remember? Aniline, phenylalanine, C6H5NH2. This is the molecule what I have worked for 5 years. Yes, with this molecule. So I know the ionization potential for this, and I have worked with several other molecules along with this. So that ionization energy less than 8 electron volt, just 7.82 approximate. So less than 8 electron volt. That means if we give this ultraviolet light, one electron can eject from this NAD molecule. That means if we can give 2 photon, that means 2 photon, you are not familiar with this term. Is it? Yeah. Photon? Photon. Yes, you are familiar with the photon. That means 1 quanta, or if we give the wavelength, whatever the wavelength, that means 266 nanometer. This is the one wavelength of the light. So if just only one shot of this laser comes to any molecule, that will give you around 4.66 electron volt. Maybe you can count to 1239 divided 0.85 divided by 266. That can be give around 4.66 electron volt. So if I can put one lens in front of the laser, lens can focus. You are familiar with the lens, is it? So if we put one lens like this way, and we are giving some light, and that light can come at this point, is it? This is the focal point. So what happens here? The thickness, that means the total beam is coming at the center or certain point. That is the focal point, and the intensity of this light is very high compared to this. Just we had a very big spot or bigger spot, and we are making it very smaller spot, so that all the intensity of this light is coming to just certain point. So if here you have the laser intensity maybe 100 millijoule per pulse, that can give you 100 joule per pulse. And you can have 100 millijoule per pulse, that can give you 100 joule per pulse. So that the intensity can be increased quite a lot. So if we use these types of combination, and we can make the multi-photon. That means the laser intensity can be increased quite a lot. So it can absorb, the molecule can absorb many photons at the same time. I have given just single shot, but we are set up in such a way that it can increase the laser intensity very high, so that it can have the possibility to absorb many photons or many light at the same time. So if it can absorb more than one photon, we call it multi-photon. So if we can absorb 2 photons at least, that will give just multiplied by 2. That is enough to remove 1 electron from this molecule. So that means this UV, this is enough to remove 1 electron from this. So if you give this energy to this one, what will happen? It is completely gone away. So all the bonds. Normally we can have the bond like this. This is phenyl NH2. This is so it can break up here. Even it can break up something here like this way. So that means what I have mentioned, that depending on the energy, all the molecules will behave how much energy we are applying. So high energy source produce breaking of bonds, that means X-ray, gamma ray. If we apply this energy to the molecule, it can decompose the molecule. Then medium energy source excite electrons, UV visible, already mentioned. So just it can excite, already what I have mentioned, for UV 266 2 photon of 266 can just eject 1 electron, nothing else. It cannot decompose. So if we give even lower energy, low energy source produce vibrations in chemical bonds. What I have mentioned that infrared, and very low energy source produce rotation of the chemical bonds. Okay. So rotation of the chemical bonds, what does it mean? If you have some HCl molecule, yes.
So this is can we increase the energy level of the light source, like can we get infrared light into UV?
Yes, possible. Because infrared we can make, we have different types of crystals. So once we are generating this light, this is our visible light, we can double it. That means if we can double the wavelength for this one, this is called frequency doubling. Frequency doubling, this is red, is it? This is red. So the wavelength of this one may be around 680 or 700 around. If we consider this is 700 nanometer. So if we can double the frequency of this light, that will give you 350 nanometers. We have some crystal already available in the market, and I have used many times. So that is possible. So if even we can frequency double this one also, that means that will give you around 175. Now you can assume what is the energy for this one, this one, this one. The energy for this one will be around 1.2 electron volt, no sorry, maybe 1.6 or 7 electron volt. That will be more than 3 electron volt, 3.55 approximate, and that will give even double 3.55, that means 7 electron volt. So we can convert IR into UV also. That is possible. So any more question? Okay. Very low energy source produce rotation of chemical bonds. What I have mentioned there, rotation. If you have HCl molecule, this is a hydrogen and it has bond between chlorine. So it can stress or compress. That will be the vibration. Is it? It can, this is a covalent bond. Is it? So it can, this is not always fixed. What is the wavelength? Sorry, what is the length of the or radius of the molecule? So it always just stress and compress, like this one. So, but sometimes if we give certain amount of energy, very little amount of energy, in that case, it can rotate like this way. It can rotate the just like this way. It can rotate. So that is very small amount of energy is required because this is a linear molecule. So it can rotate very easily. Okay, microwaves and radio waves, if you give that types of wavelength, so that can help you to rotate the molecule. That are the energy range what we can use, types of radiation, what nuclear and types of transmission, from where to where it can excite the molecules or electrons. X-ray, inner electron, I have shown, already have removed it. If we give X-ray to the sodium atom, it can take up electron from the first shell. I have mentioned for aniline that we can remove only 1 electron by giving 2 photon of 266 nanometer. But if we give X-ray, we can take electron from the inner shell of sodium. Not only sodium, most of the elements what you study. So if you can understand or if you can study the molecular structure. If you want to study the molecular structure of any molecule, you need to study the X-ray spectroscopy. In that case, what you can do, you can excite or you can take out electron from the core of the molecule. So it can give the pattern. That means, well, I should draw again. Let us. This is our solution. So this is 2 electrons. This is now. If you have or if you apply X-ray to this sodium, this electron can be ejected from here, 1 electron from the core. That means inertial. It can eject 1 electron from the. So where it will go? Somewhere in the last step. Okay. So if we put X-ray, that is very high energy, to this sodium atom, what will happen? It can eject 1 electron from the inside or inner shell of the atom, and then if you remove the X-ray, what will happen? Yes, it should go back. Now, how it will go back? Just yes. So that will emit the light. That means you have given X-ray light to this atom, and it is getting out of the electron from the inner shell by absorbing light. So now, if you remove the X-ray, that means you are not giving light anymore. In that case, the electron will come back to the inner shell once more. If it go back from outer shell to the inner one, you will get some radiation. That means corresponding energy. How much energy it is releasing, based on that, it will give you some ray or light or emission, so that you can get certain wavelength or certain light. And then if it was excited, or if the electron came back here, in that case it will go back to the first shell again. So the energy from here to here, it needs to reduce more, or it needs to release more energy. So it will give, not like this way. So it is coming from high level to ground level. Another one in the medium is coming back from. So first we have excited from here to here, or from here to here with the X-ray. So it will come back to the ground state once more, and when it comes back to the ground state, it will release some energy as a radiation, and we will get our detector system or the instrument will collect that radiation or emission. So that will correspond to the structure of the molecule. What molecule we are analyzing. So we are not going to learn anything more about the X-ray. So just up to this, and then sorry, here different types of bonds, or what types of energy we are giving, and how we can change of spin. If you give this a small amount of energy, this NMR, USR. So if we give this a small amount of energy, this can change the spin of the electron only. Just if you are familiar with the orbital orientation, spin of the orbital electron, most of the time we write down the either this way or this way. Right? So we have 2 electrons in one orbital. So it can change the orientation of the electron. That means it can rotate the spin of the electron. So if we give this a small amount of energy, that means this energy is not enough to remove one electron from anywhere, this molecule to somewhere else. Just it can rotate. That is okay. Then this ESR also similar thing, little bit more higher energy. Then change of orientation. So what? Microwave. So this can rotate little bit more. That means we are giving in between little bit. Then configuration. That means if you give some energy to this aniline molecule, it is changing the orientation. That means a structure. Normally, if you have the aniline in the neutral state, in that case, the 2 NH2, see here, 2 NH2 will be like this way. It will bend. I have seen the structure. I can show you that structure also I have, but maybe if I display that cannot give you. But if it is in neutral, that means no charge. That means how many electron and how many proton it should be. If it is neutral state, then it will be like this little bit bent. But if it is in ionized form, that means one electron has been removed. That time the NH2 comes flat. Just flat. Along this is the benzene ring, consider like this, right? So if I draw it, this is N, this is. So it can be, maybe I can try if I can show you. Oh, maybe no, not possible. That will. Anyway, I don't want to, because we do not have more time. Yes. Sorry. Neutral distribution. Electron distribution for this. You want to know the electron distribution for this one? Okay. So that will. I'm not going yet here. So I still am here in the change in configuration. So those who are online, can you see my display?
Yes, Professor.
Okay, thank you. So what I'm going to show you here, if we give the energy visible and ultraviolet region, so that can change the electron distribution. That means where I have given the 266 nanometer, that is in the UV region. So that much energy it can change. Actually, this NH2 should have 2 unpaired electrons. So sorry, 2 lone pair electrons, not unpaired. Lone pair electrons. So if we give this energy 266 nanometer, that means corresponding to 2 photon of 266, that will give around 8 electron volt. For 4.6 to 66, that means that will give 9.32 electron volt. So if we give that much energy to this molecule, 1 electron from here, it will be ejected, because already I have mentioned that I could succeed to remove 1 electron from this aniline molecule by giving 2 photon of 266 nanometer laser. So that then, as I have shown you, this is the flat benzene ring. For neutral case, the NH2, this NH2, that corresponds like this. So that comes like this. This is neutral for this bending, and then when 1 electron is ejected, it becomes flat, completely flat. So it's saying the distribution of electron, because here we can remove one electron, there will remain only one electron. So the distribution of the electron will be changed. Okay? Okay. Same thing. That means how much energy, this is X-ray is very high energy, and then ultraviolet, visible, infrared, microwave. Again, same thing. I already mentioned that one, visible spectroscopy and diffraction. So, again, last class I tried no, I cannot. I did it when it was quite dark. Anyway, so that is the energy range or different color what we are observing. Visible spectroscopy or UV visible spectroscopy already mentioned regarding this, and theory already mentioned. So UV visible, what will be the absorbance, transmittance, loss mentioned, discussed, formula, and units. Just the units of molar extinction coefficient. Very simple. We have learned the formula. That means the absorption or Lamberts law. You can see here that this is our formula. Absorbance equal E multiplied by C multiplied by L. Therefore, if we want to find out the unit for this absorption coefficient or extinction coefficient, so just we rearrange the equation. This is absorbance divided by concentration multiplied by cell length. So absorbance, it has no unit. That means percentage. It has no unit. So we will write down this is nothing, no unit. So this is C, concentration. Concentration, units of the concentration, mole per liter, and this is L, that means length. Length just centimeter, or sometime we can consider this is meter. But as this is very small length, never we used 1 meter cell. We always use 1 centimeter, sometime 2 millimeter or 5 millimeter. Even 1 millimeter it is also available, but it is very rare case. Okay, so mole per liter, centimeter, this is the, so just if you can take it out or in the above, so you are getting mole per mole, and liter would be, per liter would be liter, and centimeter would be per centimeter. So 1 cm cube, 1 liter equal 1000 cm cube. So we can make it this liter 1000 cm cube. So 1000 mole per mole cm cube, cm minus 1. So cm cube and cm minus 1, it should be cancel out by cm square, and then we are getting cm square per mole. That is the unit for molar extinction coefficient. This is very simple. If you know the formula of the Lamberts law, then easily you can find out the molar extinction coefficient. And then already we have mentioned this, and atoms or molecules can absorb or emit energy in discrete packets called quanta. A molecule can possess energy in different forms. Okay. If you have question, you can ask me, but do not talk to yourself right now. Okay. If you have any question regarding this class, then you are always welcome. But please try to not to discuss anything except the class, and do not try to talk to yourselves. Okay. So if you give, already I have mentioned that one also. If you give some energy to the molecule, depending on the energy, how much energy we are giving, the molecule will behave, and it will store or it will stay. Sometimes it can decompose the bond, sometimes it can excite. If you have some problem in the floor, you can jump up in the table. That means you are having some energy, you can jump up. So if you, this is our normal state. This is the ground state for any molecule. So if you have some energy which is given by this light, maybe UV light, visible light, or IR light. I want that means that 5 years also related with the IR. So if you give some energy to this molecule, this is a ground electronic energy level. This energy level. So these are the main energy level, and these are the vibrational levels. So this line, this is the ground level, and these are excited energy state. So if you have some energy to, this is our ground state or the molecule in normal state. Now if you apply some energy to this molecule can jump up to somewhere else. It can go either here or here or here, or even if you give more energy, it can jump up out of the this excited state also. So that in that case it can decompose. But if you give certain amount of energy, that means that is just enough to jump up from here to here, that will go or it will be excited. So a molecule can possess energies in different forms such as electronic energy, vibrational energy, rotational energy, translational energy, what already we have mentioned in previous slides. So I'm not repeating anymore. That is different, same thing. Types of transitions. Okay, I want to discuss something like this. You have different types of bonds in any molecule. I'm going to remove that. So you are familiar with the sigma bond. That means single bond. Is it? All the molecules have single bonds. So these single bonds are very stable. That means high energy. So if you give some energy, it can excite. Maybe let us consider ACE, what is the molecule? Do you know what is this molecule? You don't know? Formaldehyde or methanol. Is it? Methanol or formaldehyde. So this molecule, if I write down properly, it should be like this. Okay. So this hydrogen and this carbon are bonded by single bond. That means this is kind of sigma bond. This also sigma bond. This is pi bond. Pi bond, one sigma, one pi. Is it? Okay. And these are non-bonding electrons, is it? Or lone pair electron. So this is non-bonding electron. So now, if you give some energy to this molecule, it can have different types of transitions. That means if you give some energy, if it is very high energy, it can absorb or it can excite. That means this is sigma bond, sigma to sigma star. If you give very high energy, that is enough to excite this carbon hydrogen bond or carbon hydrogen this bond like this way. So sigma to sigma star, from bonding electron to anti-bonding. So it can go from sigma to sigma star. Maybe I can show you some other slide that can be even better. Okay, here we have some. You are familiar with these types of structure? The energy level of different types of bonds. This is the non-bonding electron. It has no anti-bonding. Is it? Non-bonding electron, there is no anti-bonding. So anywhere, if a molecule is in bonded, then it becomes very stable, and depending on how much stable the bond is, the bond energy becomes low. For single bond, the energy is minimum. So if you want to decompose or if you want to break the sigma bond, you need to give very high energy. That means you need to go from here. That means you need to give this much energy. That means it needs to be excited from sigma to sigma star. This is the bonding sigma and this is non-bonding or anti-bonding of sigma. So it is represented as sigma star. Okay. Here we have the molecule. This is aldehyde pi bond. This the energy for this molecule. So energetically, this pi bond is little bit higher compared to the sigma bond. Therefore, this bond, that means this bond is not stable enough compared to the sigma bond. Therefore, it can be excited just from here to here. If you give some energy, you can decompose this double bond or pi bond. And this non-bonding electron, the oxygen, we have two lone pairs. So this non-bonding electron can be removed easily because it is not bonded at all. So if we give very little amount of energy, so we can remove this electron either in this pi star or sigma star, anywhere. So how much energy we are giving to molecule, based on that you will have different types of excitation. That means either sigma to sigma star or pi to sigma star or pi to this pi to pi star, so pi to sigma star like this, or this n to pi star and to sigma star. These types of transition, how much energy we are giving to the molecule and having what types of bond or what types of electron the molecule have, we will have different types of excitation. The energy absorbed by organic molecules involves transitions of valence electrons of three different types. Already what I have mentioned, that sigma electrons are present in compounds containing single bonds, saturated hydrocarbons. That is example what I have mentioned. You can have that carbon and hydrogen. I have drawn in the same region. In the display, this is formaldehyde. What I have drawn, this is this oxygen should be carbon. Yeah, because it's the same region. I have drawn. This is from my slide, not my drawing. Okay, so what we are going to see, that pi electrons are found in compounds containing double bonds or triple bonds, all of you are familiar. So if you have some unsaturated hydrocarbons like as alkene or alkynes or aldehyde or ketone, where we have some double bond, that types of electrons can be excited by different types of energy. That means pi star, pi to pi star or pi to sigma star, this types of transition. N electrons, that means non-bonding electrons, are present in molecules containing nitrogen, oxygen, sulfur. If you have any molecule containing these types of lone pair, oxygen, that means this oxygen has two lone pairs. It is not bonded to anyone. Therefore, we can have this bonding, these non-bonding electrons are represented as N electron or non-bonding electron. You can excite this electron also. So we have mentioned that what types of sigma to sigma star, N to sigma star, N to pi star, and pi to pi star. These four types of transition are possible. What I have shown here, that means sigma to sigma star, pi to pi star, and pi to sigma star also possible, and then N to sigma star and N to pi star. These types of transitions are possible. Okay. Below are the structure of acetone. This is the structure of acetone. So, what type of electronic transitions are possible in these molecules? What types of transition you can expect? Pi to pi star, because you have the double bond. Okay, that means one I am writing pi to pi star.
N to sigma star or pi star.
N to
Sigma star or pi star.
okay, sigma star or N to pi star. Any more? Sigma to sigma star. Everything is possible. Yes. So formaldehyde and this acetone, we can have all of these types of transitions because we have all types of bonds or probable excitation area or excitation region, so that we can have these types of transitions. Okay. Already I have mentioned all of them. For sigma to sigma star transition, an electron in a bonding sigma orbital of a molecule is excited to the corresponding anti-bonding orbital by the absorption radiation. To induce a sigma to sigma star transition, it is required large energy, because in the graph we have seen that we need to have this mass energy. This is our energy scale. So if you want to have excite sigma to sigma star, that means the energy gap between this is very high. That means what types of wavelength it can helpful? X-ray, not X-ray. X-ray will decompose the molecule. Just below X-ray. So UV, ultraviolet, is it? Ultraviolet. So ultraviolet, and we can mention the wavelength. That can be in next slide. You may have this. Methane contains only single carbon hydrogen bonds and it undergo only sigma to sigma star transitions. You are familiar with the methane molecule. That means we have this types of CH4 molecule. So we have only sigma bond. So if you want to have the excite this bond, then you need to give very high energy, which corresponds to 125 nanometer. That means it's around 12 electron volt. This is quite high. Okay. Then N2 pi star, sorry, N2 sigma star, in this type of saturated compounds containing atoms with unshared electron pairs, N2 sigma star, what already we have seen in case of methane or aldehyde, what we have drawn previously, formaldehyde. So that case, we may need around 200 nanometer. It requires less energy than the sigma to sigma star. Because already we have shown the graph that largest is the sigma to sigma star, and then the n to pi star, again n to sigma star. In the presence of polar solvents, the absorption maximum tend to shift shorter wavelength. That means this is our absorption for the which molecule you have mentioned. In this type of saturated compound containing atoms with unshared electron pair undergo n to sigma star transition. So it requires 200 nanometer around. Now, if you have in the presence of polar solvents, if you have some solvent, you are performing the UV spectrum or UV analysis using water. Water is a polar solvent. So in that case, the absorption can be shift to shorter wavelengths. That means it will absorb little bit higher energy. So if we need for any molecule, in this peaks in the UV region related to a small methyl, okay. Anyway, so what I'm going to say that if you are performing the experiment or the UV spectrum in the with the solvent, polar solvent, in that case, if you have non-polar solvent, you may have the spectrum or absorption at 200 nanometer. Then, if you have polar solvent, in that case, you may have the absorption around 190 or less than 200 nanometer. Okay. Then n2 pi star and pi 2 pi star. That is even a smaller energy. So that is pi 2 pi star alkenes, carbonyl compounds, alkynes, carbonyl compounds. That means aldehyde ketones. So that types of transition it is possible. N2 pi star, that is non-bonding electrons, and sigma to sigma, sorry, pi 2 pi star, that I have given some examples. Sigma to sigma star, N to sigma star, N2 pi star, and pi to pi star. All of the figures. So methane CH4 has lambda max at, that means maximum absorbing at 122 nanometer, and ethane absorbing at 135 nanometer. So all of these are the same. So I think I am not going to discuss anything more. Then all our transitions, I have given some examples. If you can read this, you can get the idea, because everything are same. If I have anything more, chromophore. In last class, I have mentioned about the chromophore. That means if a molecule have a certain portion that can absorb the light, so that can be called as chromophore. If a molecule can absorb light or some portion of the molecule can absorb the light, that is called as chromophore. Okay. So there are two types of chromophores. That means what types of absorption it can have? Single bond, double bond, many things. Okay, so today I'm going to end up here. There are different types of chromophores. What types of bond you have? Depending on what types of bond you have in the molecule, you will absorb this wavelength or corresponding energy. We are giving some example so that you can easily remember what types of bond it has and what types of absorption it should be. Double bond, carbon-carbon double bond, so it will absorb 174. Here carbon-carbon triple bond, it will absorb little bit shorter wavelength even. So these types of example. So this is the end of today's class, and I would like to take the attendance.